Well, it's good that you've been able to come to this colloquium. Our speaker today is our first external speaker of the academic year, Yufeng of Central South University in China. He's visiting for a while now in the Department of Mechanical Engineering and Energy Processes across the street from us. We're very happy to have him with us for our Math Department colloquium. He'll be talking about generalized fractional calculus and applications to oscillator equations. We look forward to hearing.
Yeah. So first of all, let me introduce myself a little bit. My name is Yufeng, as put in the slide. I'm from Central South University, China, and now I'm working with Professor Agrawal in mechanical engineering. Actually, I've been here 1 year. So that's why I can speak with little English. So I'm glad you know that. So by this chance, I'm sincerely grateful to my advisor, Agrawal, and he gives me a lot of ideas and keeps giving me right ideas so that I can have a lot of time and facilities for doing the research about fractional calculus. And I also thank the Department of Mechanical Engineering, Department of Mathematics to give me the chance. It's really my honor. And I thank my mother university, like Central South University, and the China Scholarship Council for giving me financial support when I'm living here. And special thanks should be given to Professor Sola, because we have a lot of discussion during our lunchtime every day. And Professor Xiao for allowing me to attend your lecture this summer, and Professor Kelvin for allowing me to attend your PDE course last 4 semester. Okay. And then my speech will divide to maybe 4 parts. In the first part, I was talking about fractional calculus, the very basic idea of fractional calculus, and then I will go directly to 2 types of generalized fractional derivatives and integrals invented by Professor Agrawal in 2010 and 2012 respectively. And then I will describe one model named harmonic oscillator equation, because up to now this time I want to talking about the application of generalized fractional calculus in oscillator equation, and show that which kind of new things we will find from the classical oscillator equation if we replace the classical derivative by our generalized fractional derivative. And I will also discuss the numerical scheme about kind of A and B operator. But later on, you will know that what is A operator, what is B operator. And I will show some of the numerical results. Especially, I bring one famous oscillator named the wonderful oscillator. We already published some of the results about the wonderful oscillator. So let's go. So what is fractional calculus? Even Professor Agrawal has spent several lectures in this campus. People join over there, they always raise the same questions that, what is fractional calculus? Because calculus, we always know that we know calculus including something about the one-fold integration, double integration, and n-fold integration. And we also know derivative. First order derivative always describe the speed. The second order derivative always means that the acceleration. So if you say fractional, what is fractional? Actually, fractional derivative is a field of dealing the integrals and the derivatives of arbitrary order. Okay, up to here you say arbitrary. And maybe you will say, what about 0.9? Can you show something about that? Can you explain what is the physical meaning and what is the real background meaning of the things? But right now, nobody has given the real physical interpretation about those fractional operators, such that they can have the same or similar meaning as Newtonian operator, the first order derivative and the second order derivative. But this has no influence on the application of this operator, because in my personal opinion, at least we bring one more parameter when we try to model some of the process when we want to know. Okay, in 1695, the Hobbit wrote to Leibniz and proposed a question to that. So probably our is so bright at the same as our Hobbit, right? What is if n equal to 2 in the derivative, the nth derivative? And just after
half.
What is that?
Equal half.
N equal to half.
Half.
N equal half.
Yeah, n equal to half.
Yeah, not 2.
Yeah, sorry. what is it if n equal to 1/2 in the nth derivative? And just after several years, okay, I say several near 100. This guy, I don't know how to pronounce his name. He used in a very special way during that time. Okay, today, if I know the definition about fractional derivatives, I can have the solution like derivative, half derivative about x equal to those many things, I can down to within 1 minute because I know the formula. But during that time, he has the final solution. That's really amazing. Because we know that the first derivative about x equal to 1, and the second of the derivative of x equal to 0, up to n. But the half of the derivative of x, we got the square root of pi, so the coefficient over here feels a little bit like a magic. What happened? We just do the half derivative, and then we get a pi, we get a root of pi. Okay, I will talk about later. But this is right. This is the truth.
What if you repeat it? You do it again, d half. Would you get the? What do you get? You get 1?
How about let me do it later? Because we can't do it. If I show you guys all the formula, the derivations, you will do it by yourself. It's pretty easy. Yeah. And since 1974, the reason I talk about this year is that in 1974, the first international conference happened holding in New Haven. Actually, this is a city of USA, right? New Haven. And many of the scholars over there, but it's a pity that not many mathematicians over there. The first application of the fractional calculus brought into is by one professor called Wiener and one professor called Ross from the chemistry department, I think. And during this conference, they collected a lot of papers about the fractional and its application, and published the first recent book about this topic. Nowadays, we can download this book from Google, or at least we can see lots of pages. So we can know that what is the early application and research about this topic. So now I will start to talk about something about fractional integral. So before I go there, since I want to show that the fractional integration and the classical integration has some similar things, so I will start from the integer case. So if f is L1, we can do the first integration like but to show that the second line, okay? I want to find the real point. Do we have the real point? Yeah, okay. Like this one, this is the first integration, and the second order integration up to n. So up to n, this is nothing but the gamma function. Those things are all talking about depending on the integer number n. But if we just do a little bit of modification, so mathematical things are always like this. If we do a little bit of modification, many of the new things will come. We just do a little bit of modification like here. We're using the I from 0 to t depict the notation, to add the notation. And we replace the integer n by an arbitrary number alpha, like alpha over here, and gamma n becomes gamma alpha. So the whole bunch of things, now we define it as the alpha order integration. And if the alpha over here is an integer like n, like 1, 2, 3, 4, 5, 6, then it becomes our familiar things in the calculus. So we call it the real fractional integral. So from the name, we know that those kind of contribution has been done by this two great name. And there are two elemental ways to define the fractional derivative. So up to here, you may write another question. So derivative, why we have so many ways to define derivative? Let me just draw it in a simple way. I draw a line like this. Say this is 0. If f of 0, I define it as just f itself. Say if I go right, towards the right, like 1, I say that is the first order derivative. If it is 2, I say this is second order derivative.
Excuse me. Could you please stand the line down?
Why not?
Yeah, yes. No,
the light.
Thank you.
Light and the right. So over here, I define that as integration. I just write the integration over here. Here, I say it's double integration, because this is -1 and this is -2. So if f is over here, we say it's the first order derivative. Now we want to define the fractional derivative. If I say, what happens if the derivative I define over here, say 1/2, okay, 1/2. The idea is that I start from here, f start from here. and goes up to first order derivative. If I just go directly to let the f has the first order derivative, that means I derivative it a little bit more. And we know that the integration and differentiation are a pair of operator. They can cancel each other a little bit, like a plus and a minus. Okay? So if I go up to 1, then in our mind we should go back a little bit. And if we go back, we call this operator as integration. So probably if we want to have the if we want to have the 1/2 order derivative, one possible way is that we can first go first order derivative and then go back 1/2 order integration, and then we get a 1/2 derivative. And we already know that how to define the 1/2 integration because we already generated the definition. So the same idea is that how about you just go back a little bit and then forward. So from this picture we can easily know that. That's why we say we have two elementary ways. We can either do the differentiation first or do the integration first. So if we first the integrating and then differentiation, we call it the Riemann-Liouville derivative. So this is nothing but we do the integration first and then do the derivative. Oh, okay. Yeah. So if we do the m's order, we do the m minus alpha's order integration and do the m's derivative. M minus m plus alpha equal to r. So that is the Riemann-Liouville alpha order derivative. So simply the other way is that we call it capital. The capital derivative is nothing but we do the m's derivative here first and then do the m minus alpha's integration. That means first we differentiate a little bit more and then come back. And actually, you can find this paper in Google, but I do find it's not clear to read. Okay, Capital. This guy is a little bit old right now, maybe over 80 years old, but he's really famous in fractional calculus area. Really famous. I mean, many of the big names in the scope of fractional calculus, probably some of them are the students of him. And also there are many other ways. I just listed their names over here, like a Liouville operator. Liouville operator is nothing. The Riemann-Liouville derivative is defined in the closed interval from 0 to t, okay, in the finite interval. The Liouville derivative is nothing but extend t to infinity. It's easy to remember, but sometimes it's useless. Because in the real world things, we're always talking about the variable change in the finite domain. Liouville derivative, and also Agrawal-Letternikov derivative. You can take a note about this name and try to search them later. And Hadamard, and also Reeds, and also Weil. Weil is a big name. Yeah, and also I don't know how to spell cover type. Okay. And remember, go to Google. Okay. And up to now, we have the fractional integration, we have the fractional differentiation. Now we can get a fractional. Let's get a fractional. And since we have the fractional derivatives, we have the fractional integration, it is an easy question to say that we will have the fractional differential equation and fractional integral equation. This is nothing but the fractional differential equation. And the derivatives over here is the capital derivative, start from 0 up to t, and this is nothing but the initial value problem. The thing is that we force the alpha lies between 1 and 2, so we need the initial condition and the initial velocity. The reason why we can choose such initial condition for this problem, I will omit it because it's really hard to describe so many details. So let's assume that this is okay, okay, and we can solve this equation. We can solve this equation, and the solution of this equation is very easy using the Laplace transform. She knows that. Yeah, this is one of the homework. Using the Laplace transform. And then we can have the solution equal to this much plus this much. Now, you will have some question now, what is capital E and what is capital E? Okay, what is the difference between them? Forget about everything. Just think about, this is a kind of notation, this is kind of notation, and this is the solution. But if up to this solution, if inside this solution, if I let alpha equal to 2, then what happens? This kind of things becomes cosine t. This things becomes 2 times the sine of t. That's it. What I want to tell you is that this equation contains the special case if alpha equal to 2. Because alpha equal to 2, we have the second order ODE. And the solution of the general solution of this equation is nothing but A cosine t plus b times the sine of t. So if we plug in the initial condition, the initial velocity over here, velocity over here, we get this solution. And this is the general way solution, and this is the solution for alpha equal to 2 in the special case. So I'm not satisfied with this example. I want to try to discuss the similar example. Okay. I want to extend the alpha. Try to let the alpha can bring the interval from 0 to 1 together. This example just talking about alpha lies between 1 and 2. I want to use the same expression to talking about all the things that happen for alpha from 0 to 2. And if I want to let these things from 0 to 2, I have to make a little bit modification about the second derivative condition. If I let this condition equal to 0, I mean if this condition equal to 0, then this term has gone. This term will gone because of the Laplace transform. Laplace transform, right? This term will gone. That means ut equal to this much term will depict the solution for alpha lies between 0 and 2. If alpha lies between 0 and 1, this solution equal to e to the power minus t. Yeah, e to the power minus t. When t equal to 0, when t equal to 0, e to the power minus t equal to 1. Yes. And if alpha lies between 1 and 2, this is nothing but I have done some of the derivation. Yeah, I just can't remember that. Yeah, if alpha is equal to 2, we get the solution about cosine t, just cosine t. Okay. So from this simple example, I want to show that one equation over here, right in a very general way, we take advantage of the capital fractional derivative. Then the first order ODE, the second order ODE, we can bring them together. We can talk about the first order ODE, the second order ODE in a single function at one time. And this is kind of the solution. I let the alpha value from 1.1 to 1.9. The first line is alpha equal to 1.1, second line 1.2 up to 1.9. So we can see that they are consistent if we change the alpha continuously. So now I want to talk about something about the generalized fractional calculus. Up over here, because very recently, people find that the fractional integrals and the derivatives can be defined by using another function. What I want to say is that not all the functions we can define their capital derivative or Riemann-Roelle derivative. I didn't talking about which kind of function space we need for defining the Riemann-Roelle derivative and the capital derivative. Okay. But for some function, if we cannot directly define this Riemann-Roelle derivative and the capital derivative, we may have some modification. Like some of the scholars, they think about that. If I want to define kind of fx, kind of fractional derivative, but fx cannot do the derivative, what I'm going to do, I can time some of the weight function over here, and then put the weight function outside. Then this function times the weight function becomes a little bit better. Then we can do the derivative for the whole bunch of things. That also can be regarded as type of generalized fractional derivative. So this is one of the basic reasons that people want to start and to extend the definition about fractional integration and fractional derivative. And the fractional operator can be regarded as a convolution. That's easy because from the definition we know that the integration from 0 to t, we can write as t minus s and alpha minus 1 times f of s ds. And here we got gamma of alpha 1 and gamma of 1. We say this is the Riemann-Roelle integration. This is the integration. And the t minus alpha, we can say This is nothing but 1 over gamma times T alpha do the convolution about those two functions. Okay? Yeah, so it's pretty easy to understand. The fractional operator is nothing but a convolution of this kind of power function and the kernel. And the third reason is that we want to find some of the new property. If some other kernel, we replace the kernel over here. This is the power kernel, just one type of kernel. If we replace the kernel over here, what other things will be? Actually, this kernel over here looks like the omega function, right? Probably they can be the same or they can be different because this is in a general way. This is just one typical thing. So the first type of fractional operator, we call it a K operator, A operator, and a B operator. This was proposed by Agrawal in 2010. It's in a paper published in Computer Mathematics. If you want to download this paper, probably you can search on that web, and you can see some of the things. The K operator is nothing but equal to a constant times this much thing, and constant times this much thing. If you see that this is from A to T, in just several slides before, we're talking about the Riemann-Leibniz integration from 0 to T. So here we extend to A, here we extend to B, and it says that the A and the B can be minus infinity and positive infinity over here. And we say that this is the power function and times F over T. Now we say that this is K, just a simple function, the general function like depict the kernel over here. This is the kernel. And the kernel can be anything. The only thing that we first, when we write on this expression, we write on this definition, we personally think that everything is perfect so that we can have the solution, okay? Now, up to now, we're not going to worry about the function space and the things over here. We said that if we write on the definition over here, we assume that everything is finite, over here is finite, over here is finite. So we can have the definition. This definition is nothing but directly extend the Riemann-Leibniz integration. So before we using the Riemann-Leibniz integration to define the Riemann-Leibniz derivative and capital derivative. So now we can take advantage of the K operator and the classical integral derivative over here. We can define the A operator and the B operator. So the A operator is nothing but the extension of Riemann-Leibniz derivative. That's how to pronounce it. And the B operator is nothing but the extension of the capital derivative. Say that we first do the kind of integration, then do the derivative. We do the derivative first, then do the kind of integration. So they are nothing, just the extend everything in a period way. And then the P star is another set. We say that the P set equal to A, T, B, P, Q. P star equal to A, T, B, Q, P. We just change the order. And then operators A and B satisfy the following formulas for integration by parts. I want to introduce this property here because if we start the minimization problem, we do need the integration by part formula. And the fractional integration by part formula is very nice because it changes the derivative. So if we have the second order derivatives over here, we do the integration by part. We have the first order derivative. But if we have the A operator over here, we do the integration by part. We have the B operator over here. And if we do the integration by part formula with B operator over here, we have the A operator over here. So these two operators keep the switch to each other. It's really interesting. And the second type of generalized fractional operator we call it like this. Like I put a star over here to distinguish the thing, and don't let us to get confused. So if we remove the W over here, we remove the Z over here, and replace the ZS equal to S. Then this is nothing but Riemann-Leibniz integration. So Professor Ohm said that if we can generate the things, why don't we consider the whole thing in a different time scale? So the zt over here actually like a time scale, and the w function over here just like a modification of the kernel here. So in this way, the expression looks a little bit complicated, but in this expression, we can bring as many as possible type of f over here. If the sum of f, we cannot have the Riemann-Leibniz integration, Riemann-Leibniz derivative, capital derivative in the very beginning. We can just let the f times some function, and then on another time scale, we can do kind of integration, and we call it generalized fractional integral. And we can also generate these things to some of the problem. And once we want to extend the derivative, to generalize the derivative, we need some of the we need to generalize the integer order derivative also, because we can see the weight function, kind of weight function over here. So the classical things also has to be generalized, because we want to make everything consistent, like the commutative law, the semi-global property. So the generalized first order derivative, we say that it's nothing but times the function, and we do the derivative over here and times back the weight function. We call the w weight function. We call the d over here the scale function. That means if the f is really bad, it is terrible, we put some functions over here to remove the terrible thing from the f, and then we can do the derivatives on a new time scale. That's it. And the nth generalized derivative, the nth generalized derivative, m is an integer. So this is nothing but repeat. Okay, this is the first order, and this is the nth order. We just repeat. Because we have the 1 over wx here should be wt. If we have the 1 over wt over here, we can keep cancelling this wt. So that's why we want to have the wt outside. Wt to the power minus 1. Because if we do the nth order, this wt can cancel this wt. That means we can put all the definition a little bit consistent. So the generalized fractional derivative of Riemann-Leibniz type. I say Riemann-Leibniz type. Riemann-Leibniz type is always we do the integration and then do the derivative. This is the idea of define the fractional derivative. So nowadays, many of the scholars, if they want to propose their new generalized fractional derivative, they always call it the Riemann-Leibniz type or capital type, because the Riemann-Leibniz type we always do the integration and then do the derivative. And if we call it the capital type, we always do the derivative first and then do the integration. This is why I say that there are two elemental ways. Everyone accepted those two ways. And now, since we have the fractional integration and the derivatives, we have the generalized fractional integration and derivatives, we can apply them to some of the real-world problems and see if we apply these new derivatives, what kind of things will happen. And first of those things that I want to talk about harmonic oscillator. So in classical mechanics, a harmonic oscillator is talking about like a mass, okay, a mass. We give in the force, and then the mass keep coming in and back, keep going and back, around the equilibrium point, this loop. And the harmonic oscillator always arises in many problems like the simple pendulum and the spring mass system. Okay, we do see a lot of things. But this is an ideal model. Okay, it's an ideal model. Do you have me to show that? Yeah. This is one problem, and I solved it, and I made it into a movie, so everybody can know that. Yeah. I spent one day to think about how to draw a spring in MATLAB. I said, spring is nothing, just like a sine function. Let me plot the sine function. It looks like a spring. Okay, this is the thing. The thing is that if we put the fractional derivatives over here, what is the phenomenon? What is the phenomenon looks like about these things? I want next page. Yeah. This is the classical thing, the second order derivative. And lambda is nothing but repeat some of the properties of the spring mass system. And now we can see the oscillator in the bounded domain, like we fix the initial point and the end point. And this is another famous oscillator because it's the fourth order, and many of the paper has been addressed on this oscillator. I'm interested in this one, but I never worked it out for some of the problems. That's why I listed it over here. If you guys are interested, you can have a look about it. And the reason I'm talking about the integration by parts formula about A and the B operator before is that I want to discuss the generalized fractional oscillator equation in a very beginning way, where it comes from. Actually, it comes from like the minima of this function. This is the generalization of the first order derivative because alpha lies between the 0 and the 1. So if this is just the first order, this is nothing but kind of kinetic energy. I don't know what to. Is that? Yeah, probably you understand that. And this is nothing but the energy. We want to minimize the energy. If we want to minimize the energy and fix the boundary, then we have the final shape. This shape is the optimal shape of this oscillator. And since we have the integration part formula and the Euler Lagrange equation of this functional turns out to be this way. And now we call the equation 17 the generalized fractional oscillator equation. And also we can call it just the generalized oscillator. If we know everything, if we know we're talking about fractional thing, we can get rid of some of the terminologies.
So I'm still trying to get my mind around these operators. Are there simple solutions to simple equations like d alpha f is proportional to f? Are there simple solutions to things like that?
Yes, we do have. The thing is that solve those problems always depend on some like a generalized function, some like a gamma function, beta function, and beta molecular function. We want to study some of the spatial function first, but I want to go directly discuss all the things based on numerical scheme. So we dynamically, I'm trying to talk about a little, and everybody who has the interest can go to Google or go to our classroom and then take advantage of our lecture. You will know that. But up to now, I just introduced a little bit, say that even if we generalize the things to fractional cases, generalize the fractional case, we still have some advantage method to solve the equation like this equation, right? We can solve this equation. We can have the closed form solution. We can do that. Okay. So next, I discussed some of the numerical scheme called finite difference scheme. So first of all, the domain is from 0 to 1. So I divided this domain into several parts, and this is the step size. For simplicity, I just take every step size is equal to h, and also take the kernel as a differences kernel. The differences kernel is very interesting, and also it is very important because in some of the function, it can go back to the Riemann-Roellin case. And I let p equal to 1, q equal to 0. We said that q equal to 0, there's a k operator, we just got the first part. P times something plus q times something. If q equal to 0, we just have the first part in the k operator. So in the b operator and the a operator, all of them we just have one term. It makes the problem a little bit simple. And for simplicity, also we denote the uj and fj equal as the function u and f, the value of them at t equals to tj. And now we approximate the b operator. The b operator p star, this is the right part, okay, defined by first order derivative and then do the kind of integration. This one is by definition, nothing else. And this is the concrete definition, nothing else. This one times this one. From this one to this one, because I divided the interval from 0 to 1 into several parts, then this integration I divided in the summation of all the integration in the subinterval. So nothing else. I divided the integration over here and subinterval here. Since on this subinterval it's really small, so the derivative of u I can write it as the finite first order differences, like u at this point minus u at this point over the h. And now I put the h inside over here. I say, because this is the known number, this is the known number, this is the known function. I can calculate this integration right now. If I calculate the integration times 1 by h, I call it C, because the constant C, and the constant C depends on h and depends on k minus j also. And since the uk plus 1 minus uk appears every time, and from j to n minus 1, if k equal to n minus 1, here we have un, and here we have un plus 1. So I divided this, I just simplify the whole thing and write it down as another constant w times uk and k from j to n, because we have n over here. And the c and w are given as follows. The c, we already know that c equal to this integration times 1 by h. And what I'm going to do, I transfer this integration. This integration happens from tk to tk plus 1. And tk is changing every time, right? It keeps moving. I say this is inconvenient. I transfer this integration to the standard interval from 0 to 1. I just made some like a variable transform. That's easy, and then I have it. And the wt is nothing but this one minus this one. Okay, I do a little bit calculation, and everybody can understand that. Let's go back to this equation. This is nothing but u of k plus 1 minus uk times the vector c, because c is going to change, okay? I call it as a vector. So if I write it down as u1 minus u0, u2 minus u1, u3 minus u2 times c0, c1, c2, you see? This one, I put 0 over here. And finally, I have u n minus u n minus 1. I put 0 over here. Then just to get one digital shift, okay? So that's why in the next, all the j plus 1 to n minus 1, I got c depend on k minus j minus 1 minus c times j minus 1. Because c1 over here times u1, but I also got c0 times u1. So the final u1's coefficient should be c0 minus c1. The back one minus the former one, the back one minus the former one. So you always the back one minus the former one inside, because this minus 1 is no minus 1. Just transform. The same thing happened in A operator over here. This is by definition, nothing. And this is by a property. If the left initial condition is 0, then the D1 can come across the K operator and become inside. This is the property. And then definition. And then the same technique, I put this one times 1 by h as a constant d, and then do the same thing. Call the new constant as v, and the constant v is nothing but the back 1d minus the former 1d. And finally, plug all the things into the equation, back to the equation. I have this Discrete form. So now the problem is that I solve this problem, I solve this Discrete form equation, I can have the numerical solution. If I reduce the step test even small, I can have a very nice numerical solutions. And the initial condition, u0, and the end, the boundary condition I already know. So j can just start from 1 to n minus 1, because the initial condition and the boundary condition I already know. So the first example, I constructed it like this. If you see the f is so ugly, you may guess that I constructed this example on purpose. That's true. Yeah, the f is so ugly, okay? So the analytical solution about this one is sine of pi x. Sine of pi x. The analytical solution is sine of pi x if I use this kernel. This is the differences kernel. We have discussed it with Professor Sarah sometime, right? You say that, how about if it's just as simple as t minus x? This is nothing. If the kernel is t minus x, I write it looks like a differential equation, but it is an integral equation. It's continuous, okay? It is continuous. No derivatives over here. But it is still, you see, it still has some of the oscillator behavior. And since it is continuous, the kernel is continuous, within a row of step sets, we can still have very satisfied numerical solutions. You see that when h 1 by 4, 1 by 8, 1 by 16, 1 by 32. When h equal to 1 by 16, 1 by 72, I have pretty nice numerical solution. Very nice. Convergence already. And to demonstrate the stability and the convergence, okay, I just fix the alpha equal to 0.8 and take lambda equal to 1. Take lambda equal to 1. And then this table shows that if I reduce the step size by half, and then I get the convergence order pretty close to 2. And this is nice because this is the first order problem. I just describe the discretized the problem directly, then I get the second order convergence. That's very nice. And the second problem, so still the f is really ugly. Okay, I didn't do it on purpose, so I cannot solve it analytically because you have the sine of t times the polynomial. I don't know what is the analytical solution. Okay, so I still consider the same kernel over here. So this equation is nothing but, in fact, it is an integral equation. It is an integral equation. And the integral equation. Then I solve it with different alpha. So alpha from when we can see that when the alpha is going to grow in, and the oscillator behavior is also going to grow in. So those kind of things can never be seen in the integer order systems because for the integer order system, it never had so many parameters, so that we can analyze the phenomena, the new phenomena we receive from the system itself. And also we take the alpha equal to 0.9, and we take the h equal to 1 over 1024 as the best approximation. Okay, and every step size, so we make a comparison with the numerical solution obtained by h equal to this much. We still have table over here. So if I reduce the step size by half, and I put h equal to 1 over 1024 as the kind of analytical solution, I use I made a comparison between this solution with these all solutions. Then still I can get kind of a second order convergence. This is for the continuous kernel. It is a general conclusion because solving the integral equation with continuous kernel, somebody published a paper about the water type equation. If the kernel in water equation is continuous, the convergence order always get a little bit improved than the singular water equation. And as the third example, I can see the kernel like this. Okay, this kernel is nothing but the linear combination about two type of singular kernel. Because we know that alpha minus 1, this is nothing but the kernel appears in Riemann-Duval integration and Riemann-Duval derivative. So I made a combination of them. I say that just like consider two fractional derivatives at the same time, because this is linear and I can divide them by 2. And now I also change a little bit the initial and the boundary condition, because I set f equal to 0. I set f equal to 0. The fractional differential equation always has the property that if the f is going to be 0, this is also the equation. It means that we never put the energy into the oscillator. And since the kernel is singular, if we take the initial condition is 0 and the boundary condition is 0 also, then we will always have the 0 solution. That means the things will always stable there, never move, because the energy is going to be 0. That's the natural state. So I just take the boundary point for at 1 equal to 1. Then the mu is nothing lies between 0 and 1. Then I solve this problem. The first problem is the first solution case is that I fix everything except the alpha. So I change the alpha 1 and alpha 2 like 0.1, like the first part a little bit. Okay, so first part a little bit less, and this part a little bit large. And then increase 1, decrease 1. I see kind of oscillation behavior about this system. when the alpha 1 gonna be increased, it's gonna be like this, and then change to this, change to this, and then change to this. Okay, it's very interesting. The stability. Okay, stability. I also do the same thing. Take the mu equal to 1/2, alpha 1 equal to pretty close to alpha 2, but I never take them the same. And then lambda equal to 5. Over here I take lambda equal to -5. So I change the lambda over here. And this, since the kernel is singular, so from this example, as we reduce the step test by half, we just see the first order convergence. And the convergence is a little bit less than first order. So the observation is, as the step size is reduced by half, the area reduced close to 1/2 eventually. And we adopted the continuous kernel so that in the former two examples we see second order convergence. But with the singular kernel, we just see the first order convergence. Because it's the second order convergence get lost in computation because of the singularity of the kernel. That's my conclusion. Maybe this is wrong, but during all my examples, all my test examples, I never found that with singular kernel, this scheme can approach second order convergence. It's maybe a little bit larger than 1, but never approaches 2. Okay, here we got a little bit larger than 1, but never approaches 2. If during the test example, if you say this scheme is second order convergence, probably you have to see sometimes the convergence order is a little bit higher than 2, it's a little bit lower than 2, but pretty close to 2, like 1.9, 2.1, like that. And in case 2, I fix the alpha lambda, I consider about the mu. Mu is nothing, the coefficient in front of the kernel. So if I change the mu a little bit, then it has some of the influence to the oscillation behavior, but it's not that larger than the alpha. Because alpha is the alpha order. If we change the order, it looks like it totally changed the structure of the oscillator. If we just change a little bit of the coefficient, then that's okay. The shape is going to be changing. And the third case is that we fix alpha and mu and consider lambda. In the classical oscillator, lambda is nothing, depict the frequency of the oscillator itself. So different lambda totally depict different oscillator. So that's what we have done. If we change the alpha from -2 to -16, we see totally different shape, totally different. And we say that if we increase the lambda over here, the frequency will keep increasing too. I do see some of the solutions if we say lambda equal to like 250. You'll see the things like this, very dense, and then very dense. And now we go to study the wonderful oscillator. Wonderful oscillator is proposed by scientist Wonderful in 1927, and it is famous. Many of the authors, once they write down a book about dynamical system, they keep talking about this oscillator. This oscillator is very beautiful because it has the things over here. It makes the system makes this oscillator can absorb the energy when the amplitude is lower, and keep losing the energy when the amplitude is a little bit higher. So that means those kind of systems always process the limit cycle. Limit cycle is one of the interesting topics in dynamical system we want to talk about. So that how many limit cycles the system has, and what is the position, and what is the stability of that. So in what follows, we will focus on talking about f equal to 0. Because if f is non-zero, that means we always give the oscillator some extend force. That's really hard for us to analyze the future behavior of the oscillator. So we just force the f equal to 0. Let f over here equal to 0 always is 0. Yeah. This is the limit cycle. This is one typical limit cycle about the integer or the wonderful system. Okay, I let mu run from 0 to 10. Then we can see that the shape of the limit cycle is going to be changed. And when I first observed this phenomenon, one natural question is that I do see that this part keep going up. Okay, keep going up, keep going up, and keep going up. I proposed one question to my tutor. I say that when these things will get broken, that means when, for how large the mu is, then the limit cycle is going to disappear. And he said that maybe never. I say no. When I program the things, mu equal to 100, then it's going to broken. Sometimes mu equal to maybe 20 is going to broken. It depends on the step size I select. But during that time, that was 2 years ago, okay, I have no idea about the background theory about this system. I just think about that. It's interesting because we change the parameter, then the shape gonna change it, and it become loose string. Okay, it didn't have, okay. And using the B-operator, we can also generalize the wonderful system to a general way. And here we write down 3 typical things. The first thing is that we replace the first derivative over here by B-operator. So this becomes more general. We have the fractional derivatives over here, but we have integer the second order derivatives over here. And the second class is that we replace the first order derivatives over here, and then we replace the first derivative, one part over here, and then using the integer the first order derivatives over here. The third type is that we replace all the derivatives by B-operator. And of course, we can replace all the things by A-operator and by A or B-operator. We have many cases. But I just want to talk about those 3 typical things. And the alpha lies between 0 and 1. Alpha lies between 0 and 1, all of them. And D is the classical derivative operator. So if I take x equal to u, y equal to this one, this equation can be written in a discrete form way, like this. It's easy, because this is the first order derivative, and this is the thing, and this thing, w, we have already discussed all the things before. So, if I replace the x equal to u, y...
Do you know the limit cycle exists, or are you just numerically trying to reach it?
First of all, I can tell you that I know there is a limit cycle. Because the kernel, I will tell you later, okay? Because of the kernel. That's why I 99% believe that there is a limit cycle.
99%.
Yeah.
You proved it?
No, I never proved it. But
that's the question.
That's a very good question, actually. I will discuss later. That's very interesting. And the tab 2, the tab 2 thing, we can discrete it in this way. And the tab 3 thing in this way. This is nothing. We just borrowing the same thing, how to discretize the B-operator. We plot the things over here. Then we have the equation. The only thing is that once we compute the whole thing, one tiny thing is that since we have the xn over here, so when we goes up to this equation, whenever it appears x, we use the xn. Because we already calculated xn, we use the xn. We already have xn, so we use xn. We have xn, we use xn. The reason I want to point out these things is that in the integer second order equation, if you want to solve this kind of equation, even though we have xn over here, I can still use xn minus 1 over here. That means this scheme is totally explicit. It's totally explicit. In the right hand side, I always use the forward step thing and then get the present state thing. But in fractional things, whenever you have the solution, the latest solution, use it. Otherwise, we will make trouble. Because I made a mistake before. I don't know how to prove that either. But this is the thing I do realize. Okay? So I will use those kernels. You use those kernels. The first kernel is the exponential kernel. Exponential thing is nothing. If we think about the Taylor expansion, okay? Exponential thing equal to 1 plus something times 1 over 2 times something squared plus 1 over 6 times something cubic. Taylor expansion. So if we can see the exponential here, kernel over here. Okay, let me this much time. if I regard the whole thing as totally the whole thing equal to 1 minus t minus s plus t minus s squared, and then plus t. Okay, is that correct? Yeah, looks like the Taylor expression. Because when I want to select the kernel, like the exponential kernels, the first thing that the exponential thing is infinitely times differentiable. We can always do the derivatives about this kernel. The second thing is that if we do the things numerical, we try to take the first 100 terms. It appears this thing. This is nothing but 3 minus 1. This is nothing but 2 minus 1. So this is a kind of a kernel. Looks like the second order appears in the second order Riemann-Weyl integration. Because in Riemann-Weyl operator, we do have the t minus s times some of the alpha minus 1 like here. So that's the reason first of all, I said that how about we try the exponential kernel. The second type of kernel we call the modified fractional power kernel. Like this is nothing, we just put a constant over here. The reason is that this constant can a little bit change because a equal to 1. If a equal to 1, this is a constant. If the kernel is a constant, there's nothing. It's the constant that goes on. Then the kernel has disappeared. If the a equal to 0, this is nothing, but goes back to the Riemann-Weyl case. So this is also a little bit of modification. Not that much really, just our mind. So we calculate the whole thing and print the dynamicals. So if mu is really small, as we see in the integer of the wonderful system, if mu is really small, the limit cycle, the shape of the limit cycle looks like a circle. Looks like a circle. When the mu is going to increase, some part of the limit cycle goes up, okay, and then like we just stretch the whole thing. So the mu is a little bit small. We do see some of the limit cycle looks like this, looks like the circle. And if mu goes a little bit large, like equal to 1, then like somebody hanging over here, and then put the circle a little bit, change the shape. And if the mu, everything is the same, okay, everything is the same, we just change the mu. And if we change the mu to 5, then the shape is going to change a little bit more. So actually right now I want to ask the question you proposed. Because we take the continuous kernel, I know that the continuous kernel never have destroyed the structure of the oscillator system because it's non-singular. It never brings something like worse or terrible into the oscillator. So if the oscillator in the very beginning it has the limit cycle, finally it should preserve the things also. That's what I guessed in the very beginning. So I say if I take the continuous kernel and then I see what happens, and finally I see from the exponential, take the exponential kernel, I do see the limit cycle. This is the limit cycle, and the shape is a little bit the same, or a little bit similar. If we take the modified power kernel, because we take the constant and modify it, so the limit cycle is also exists, and the shape and the whole thing is pretty like the same thing we observed from the integer of the wonderful system. And this is the same happening from a little bit lower mu. When the mu increases to 1, the shape is changed to this one. When the mu equals to 5, the thing is changed to this one. I will go back to this figure because I observed so many meat from this figure. So many meat. And this is from type 2 with exponential kernel. From the mu very small. We see this is stable, go to the equilibrium point. These things never happen in wonderful system. In the wonderful system, if mu larger than 0, and we can take any initial condition other than the equilibrium point, then the solution will approaches to the limit cycle eventually. That means we say the equilibrium point, the limit cycle in the integer of the wonderful system is stable both from inside and outside. So, but in this case, we know that what is the type 2 wonderful system? We replace 2 places by B-operator. So if we replace 2 places by B-operator, it will totally change the whole thing. The reason which is we will observe the limit cycle in the first class is that we just replace 1 place with the B-operator. So the limit cycle is over there. So here, if we replace 2 places with B-operator, then we lose the limit cycle when we use the exponential.
What is your alpha you choose here when you use the operator, the fraction?
Alpha equal to 0.9.
0.9.
Yeah. And over here, we do see, and actually here, this is not the limit cycle again. I just show the finite time because it converges to 0 so slowly. And then equal to 5, then finally we get limit cycle. So it's a little bit different. I just here report the phenomenon. So if we consider the type 3 generalized the oscillator, the type 3 is nothing but we replace all the derivative with B-operator. Then if mu is really small, we have the limit cycle pretty close to a circle. And if mu increase, we have the limit cycle. And the initial condition, the speed of the initial condition approach to the limit cycle, the speed is improved. Okay, and before the speed is a little bit slow, and here the speed is a little bit fast. And if we keep increase the mu, the speed is pretty fast. Just go around and then approach the limit cycle. So I say that I want to go back to this one. This one.
Excuse me. I know that people do have some other obligations. It may be a good time to wrap up this.
I will finish in 5 minutes. Okay.
I don't know that 5 minutes is going to do it.
Shorter.
Shorter?
Almost immediately.
Yeah, almost immediately. There are people that have other obligations.
Okay. So I just want to talk about one sentence there. This is very interesting. This is very interesting. Here I said that this is nothing happened about the fractional gradient got growth. Fractional gradient field get growth. Because in the integer wonderful system, you will never see this phenomenon. You never see, I claim that you never see these things happen when f equal to 0. But even f is 0, in my case, I do see the same thing. So that means the fractional gradient do happen in some integer of the system if you replace the fractional derivatives into the system. And those fractional gradient field, we have no idea about that. No one published even one single word about these things. That's what I want to say. And this is the 4 major conclusions. We will introduce the 2 types of fractional derivative operators by Agrawal. I want to claim that this belongs to him. And we will also talking about the applications about to harmonic oscillator and wonderful oscillator. And we see the second order convergence if the ODE with exponential kernel or that means continuous kernel, and the first order convergence with singular kernel. That's part of the work I have done before, and this is some of the publications in the very lesson. It appears like people like it because when we send our papers out, it's just 2 or 3 months. When the reviewer says that this is very interesting, and we do see the same thing, and we never see the same thing in integer case, they are interesting. Thank you all.
Perhaps along the time questions would be better saved for the time of refreshments, which I hope you'll all join us upstairs. Thank you.
Thank you for coming.